Okay, this is numbers 13 and 14 from the review for the part 1 day of the final. So I'm going to start off with part A right here. And this is an exponent uh, on one side with a base and a base with another exponent on the other side. Before you jump straight into trying to do logs, you should always check to see if you can get the same base on both sides. So one of the things I would check is to see what these numbers could be broken down into. For example, 3, if we leave that alone, we could also write 27 as something that is 3. It would be 3 to the third power. You would still have the negative 2x on the outside because we haven't done anything but adjust the 27. This then is 2 powers on one base, so we would multiply. So now I have 3 to the x plus 1 equals 3 to the negative 6x. Once you have a single base on each side, if they match, you just set the powers equal. So then I would subtract over the other x. That makes that negative 7x. And then to get x by itself, we would divide by negative 7. So x is equal to negative 1/7. That's the same situation you're going to encounter in B part, except we have a couple things going on. This is a 4, but it's in the denominator. So if I want everything to be a 4, I'm going to have to move that guy up. If you move him up, you change his exponent, which right now is a 1, to a negative 1 because it has moved locations. Bring down the x plus 6 that was on the outside, and 64 can also be written as a 4. It'd be 4 to the third power, and then 2x plus 8 on the outside. Go ahead and do power, which is these two groups. You distribute because this is multiplication. So I now have 4 to the x for the first part, 4 to the negative x minus 6, because you distribute the negative 1, and this equals 4 to the 6x plus 3 times 8 is 24. Now the problem with this one and why this is a little harder than A is there are 2 4s on the left. We need it to be just 1 4. So this is like just doing x squared times x cubed. You keep the base the same and you add the exponents. So that would just be 5. So we keep our base the same and we add the exponents. Well, x minus x is 0 x's, so that's nothing, and then we'd still have our negative 6. Now we have one base on each side, so we set the powers equal. Subtract over the 24 and get negative 30. Divide by 6. So this one is negative 5. Okay, let's move on to C. C is going to be the cause of us not being able to use this property anymore, where we can't get just the same base on each side. The first thing you should always check for when there's an exponent that is attached to a base and you're trying to solve for that, there doesn't need to be anything else over here. So we're actually going to divide the 10 over first. So this is now 3 to the x plus 2 equals 85 over 10. You could reduce that now if you want. In fact, I think I will. 5 goes into 10 2 times, and 5 goes into 85. Let's see, that'd be 1 with a leftover of 3, so 35, so 17 times. Notice, this is to the first power, 17 over 2. This is 3. You're never going to get those bases to match. It is not any way to make those both a 3 or both a 17 over a 2. So what we have to do is incorporate a log. Now the typical thing to do is to just take a log of both sides. That is legal as long as you use the same log base. So I'm using just generic log, which is base 10. On this side right here, we now have this power up here that can be brought to the front. Remember, that's our rule about logs. So that's a property. So now I have x plus 2 times log 3 equals log of 17 over 2. I would distribute this binomial and the log together, so that's x log 3 plus 2 log 3 equals log 17 over 2. I would then try to subtract this 2 log 3 over so that only the x part will be on the left side. So now I have log of 17 over 2 minus log of, or excuse me, I should have a 2 in front of that log, minus 2 log 3. So the last step would be to divide everything by log 3. And honestly, you can do more to clean this up, but I don't care about cleaning it up. Some people are very nitpicky about making it a single log by using the properties of subtraction goes to division and division. Yeah, I'm not picky. So if you get to this point, we're good. Okay, so that would be my exact answer. If I wanted a decimal approximation, I would just plug that into my calculator. Okay, so that leads us into D. D is kind of similar because there's no way to get the same base on each side. D is a good option for a bonus, by the way. So because 6 can't be a 4 to any power and 4 can't be made into 6, and neither one of them can be made into anything smaller to the same power, we're going to take a log of both sides again. To get those x's out of those exponents. So we'll pull the 2x minus 3 to the front, and they'll have the log 6 out there. And 5x plus 8 will come to the front, and we'll have our log 4. We need to distribute everything, so this is 2x log 6 minus 3 log 6 equals 5x log 4 plus 8 log 4. Get the ones that have the x on the same side together. So I'm going to subtract over that 5x guy. So I'll have 2x log 6 minus 5x log 4. Then this one does not have an x, so I'm actually going to move it to the other side. So I still have my 8 log 4, but now over here I'm going to have a plus 3 log 6. I can pull an x out of both of these. That's the whole point of getting them together. Bring everything else down. My last step would be to divide by this parentheses to get x by itself. So we actually get 8 log 4 plus 3 log 6 all over 2 log 6 minus 5 log 4. And again, you could clean this up, and I did on the answer key. I did a couple different things with properties, but I'm good if you get to this point. Okay, so let's talk briefly about the ones that have the logs in the equations already. If you have the same log on each side and you only have one log on each side, and everything's inside that, then you can set these logs insides equal to each other. Now, you do have to check solutions when dealing with logs. Remember, your arguments, which are the parts inside your logs, always have to be greater than 0. So if I solve this, I would subtract over the 3x and subtract over the 9. So that would be negative 26, and then divide by that. That would make that negative 13. And right away, this is going to fail because 5 times negative 13 plus 9 is not greater than 0. So because that doesn't meet the requirement of the inside being greater than 0, we have no solution. Okay, this one's a little different because there's not everything a log. If everything's a log, you try to combine it down till you get one log on each side and you set the parts inside equal. If you have a number that's not a log, you can't use that drop the log property. What you have to do is get all of your logs on one side. So we'll add over the log 2 of x plus 7. And then you want to use a property to turn this into one log, and then we're going to convert it to an exponential because that's the only way to solve this if nothing, if not everything is a log. So plus turns into times. So we'd have log 2 of x plus 3 times x plus 7. We'll go ahead and work that out. That's log 2 of x squared. A 7x and a 3x would be 10x. And a 3 times 7 is 21. Now, you cannot set this equal to 5 because this has a log and this side doesn't. So you have to convert it by doing 2 to the 5th equals all of this. So 2 to the 5th equals x squared plus 10x plus 21. Use your calculator. 2 to the 5th is 32. And if we subtract that over, we get, I believe, negative 11 at the end. that factors into an x minus 10 and, or excuse me, 11. It'll be a, wait, hang on, let me stop myself. I'm going too fast. It'll be an x minus 1 and an x plus 11 because we have to add to 10 but multiply to negative 11. So minus 1, positive 10. When you solve that, your two possible solutions, I'm going to put them up here, are x equals 1 and x equals negative 10. So you need to go back and check them. 1 plus 3 is definitely bigger than 0 because that's what we have to check. 1 plus 7 is also bigger than 0, so I know that this one's a solution. Negative 10 plus 3 is not greater than 0, so that means this guy is out. So only one solution there. Similar thing for G. You've got subtraction though between them, but this side does not have a log, so we have to do the combining property. When you have subtraction, it turns into division, the first log's argument over the second log's. Then we still do our spiral to turn this into an exponential. So 3 to the 4th equals x plus 7 over x minus 1. 3 to the 4th is 81. You can think of that as 81 over 1 if it helps. We cross multiply. So I get 81x minus 81 equals x plus 7, because multiply this times this and this times this. I would get my x over by subtracting it. Add my 81 over. So that's 88, and I get 88 over 80, or 11 over 10. So we need to check that. 11 over 10 plus 7 is definitely greater than 0. 11 over 10 minus 1 is also greater than 0 because this is just a little bit bigger than 1. So this is a good solution. Now all that leaves us with is number 14, which is a just seeing if you have understood that certain tables have properties. If you're linear, you will increase by the same amount of adding every time that you go up. If you are exponential, you will use a multiple of the same type. So in other words, to go from one y to the next, you multiply by the same thing over and over again. And if you don't fit either of those models, then you're a neither. So look right here. Notice how each of these is going up by 1, plus 1, plus 1, plus 1. That's consistent. If this side is also consistent by adding, then it would be a linear equation. This one up by plus 1, but this one up by plus 3. This is not consistent. Now that means it's not linear. Okay? To check if it's exponential, you have to ask yourself 2 times what equals 3? Well, that's not something normal. 3 times what equals 6? That'd be 2, but 6 times nothing that we know equals 9. So there's not even a multiplication pattern here. So there's also not the exponential relationship. So that means that this case would be a neither. This one, notice it's hard to tell from the first one. All of these are still going up by 1, but this is times 6 to get to 1, and you times by 6 to get to 6, and you times by 6 to get to 36, and you times by 6 to get to this. So notice it has a multiple of 1 extra 6 each time. So that means that this is the function y equals 6 to the x, or if you want to put it in function notation, and this would be considered exponential. So that would be the function, and that would be exponential. So exponentials always have the same multiple over and over again. Now, because we didn't have one on the review, I'm going to make up a linear one real quick so that you know how to get the answer for that piece if you were given one. So if we have negative 1, 0, 1, 2, and 3, let's say that our f of x is 2, 4, 6, 8, 10. Notice these are all going up by 1, and these are all going up by adding 2. When you add the same number each time, you're actually linear. So the way you get your answer is, remember, this guy is your y-intercept because it's a 0. And we'll give you a chart that has that y-intercept in it. So all you need is your slope. So to get slope, remember, you pick 2 points. So I'm going to use 2, 8, and 1, 6. So I'm going to list them first. and 2, 8. And I'm going to do the slope formula, so that'd be 8 minus 6 over 2 minus 1, which is 2 over 1, which is 2. So I know my b is 4 and my m is 2. So this would be f of x equals 2x plus 4. So if it was a linear function, this is your y-intercept, or b, and you just need to use 2 points to get a slope. If it's exponential, you just need to figure out what did they multiply by over and over again, raise that to the power of x. And if it's neither, you don't do anything. So if it doesn't have a consistent pattern at all, it's probably not going to be either one. So that is it for the video, and I hope this is helpful for you guys. I'll see you tomorrow at the exam.